Friday.
Okay, Friday. Make sure that you know though, because it's not today, it's not tomorrow, but it's Friday.
Yeah, I can't memorize the verse, but I memorized the entire exam schedule.
Alright, go ahead and have your homework out. Welcome, Quentin. Be sure to contact the school if you need to about anything, but I hope you're doing alright. Alright, go ahead and have your homework out. We're doing anything from chapter 6 to chapter 7, because that's mainly what we're focusing on today. We got through, Ethan, you got a question? Alright, we got through chapter 9 and chapter 8 yesterday, so that's a good review for that one. So now we're going backwards in the book. So if you want to focus on chapter 6 and chapter 7, that would be best for you. Thank you.
I actually have my paper here too.
Yay! Thank you.
And I messed up. I think I have 2-inch margins.
You're what?
I think I accidentally put 2-inch margins.
Great.
Well, format error.
Because I put 1 and I clicked OK, and I don't know if it.
Did you do Times New Roman 12 font?
Yeah. I clicked. It put. So it said right and left when you go to like paragraph with line spacing.
Mm-hmm.
It is 12 point font, right?
It's 12 point.
Clicked advanced or whatever, and it said right and left. I put 1 inch. I clicked OK and it did that. So.
Alright, so let's go ahead and look what?
Looks kind of dirty.
It's okay. Format errors. Alright, so let's go through the questions. Number 1, define energy. We'll start with Jamie. Welcome, Jamie.
Energy is the ability to do work.
That is it. Alright, in thermodynamics, what is a system? Alright, Chris, look across to you.
System is the known universe and the surroundings of unknown.
Good job. So basically it's everything. Okay, so it sounds like you started right, but then the second part sounded kind of weird. So what's the system again?
The system is the known universe and the surroundings are the unknown.
Not quite. Okay, based on what you're talking about in that one. Yeah. Alright, what have you got?
System is a portion of the universe being studied surroundings is the remainder of the universe.
Yeah, so that's what. So with the idea of the known universe, or what you're looking at for your experiment, that's the system. Surroundings is everything else. So it's not really unknown, but it's everything else like outside of your environment. Alright, number 3. Does gasoline in a car's tank represent kinetic or potential energy, and why? This is a little bit weirder. Jamie?
I'm not sure on this one.
Okay.
Gasoline in a car's tank represents kinetic energy because the energy of motion is associated with it.
Yeah, okay, and that just, but if you have gasoline just sitting in your tank, what type of energy is that?
Potential.
Potential energy. So that's the answer I wanted you to give in the book, but I understand again, yeah, once it's actually reacting, then yes, it is the idea of kinetic because it's causing motion. But it's the idea of, okay, what's it just in the tank? That one is potential. Number 4, what is a state function and how does the concept relate to internal energy? This one's also a little weird, Ethan, so we'll eat of it.
Before,
Number 4.
a state function is that its value is determined only by the state of the system.
Mm-hmm. And how does the concept relate to internal energy?
I just put something out over here. I did not know what to say because I did not know what I was talking about.
Alright, Chris, what you got?
I didn't know what I was talking about either.
Okay, Jamie, what you put?
For the whole thing or just the last part?
He got the first part right. What do you got for the last
I
part?
put internal energy is a state function.
Mm-hmm. Yeah, that works. And that the change in internal energy is determined only by the initial and final stages. So basically it just says, okay, what is it at this exact point? Doesn't matter how long it took to get there, it's just there at that exact point for it. Number 5, in what direction does heat always flow? Ethan, back to you.
Heat always slows up. Heat always slows up. Right? Up? Doesn't it go up?
Okay, you're thinking of heat rises in the room. So if I have
No, I thought that was.
alright, so if I have a okay, well like my cup of coffee. Alright, my cup what?
It's always go right.
Alright,
What?
my cup of coffee right now, is it gonna stay permanently hot?
Yes.
Okay, what's gonna happen to my cup of coffee?
It's going to get colder.
It's going to what?
Get colder.
Yeah, why?
Because heat is leaving.
Yeah, because heat flows from high temperature to lower temperature. So that's the answer that I wanted for it. Now, hot air rises because hot air is less dense than cold air. That's why in the room the hot air goes up. But that's all I wanted for it. Alright, number 6. Name the... I forget it does that. It's like every 2 minutes it does it.
Sounds like NCIS.
Just leave that alone.
Reminds me of
Alright, number 6.
Tomorrow Galaxy.
Alright, make sure you pay attention, Chris. What is the SI unit of energy, work, and heat?
SI units are QW joule.
What is it?
QW joule.
Okay. Oh!
Road danger.
Okay, it wanted just the S. Okay, you gave the symbols for it. So it just wanted just the SI unit. How do we measure energy, work, and heat?
Energy is
how do we measure it? Like, it's not grams, you said it a minute ago.
Jewel?
Joule, that's all I wanted for it, but yeah, good job giving the symbols for it
Saved
too.
my life.
Number 7, what is the specific heat of a substance and how is this how is this quantity symbolized? Jimmy.
The specific heat of a substance is the heat required to cause a unit rise in the temperature of a unit mass. This quantity is symbolized with the lowercase c.
Now remember, this is in thermodynamics. Anyone else remember what other value is represented by a lowercase c? This is in a later chapter.
Lowercase what?
Lowercase c, what else does it symbolize? In thermodynamics, it has to do with a specific heat.
I know.
Kilometer?
Nope.
I know.
Calories?
Nope.
Uh,
I mean, I guess, yes, it could be
Calculations?
There's another chapter that we've talked about where the lowercase c represents something else.
I know.
We'll start with
Speed.
speed,
Speed of light in a vacuum. So we also use lowercase c.
aka time travel.
Not quite yet. Alright, number 8. What is the purpose of a calorimeter? Alright, Chris, you're kind of leading into this.
A calorimeter measures heat flow.
That's it. Alright, what is heat of reaction? And why might this quantity be important in such fields as power plant engineering? So again, a kind of more weird one. Alright, Jamie.
If a reaction is the total amount of heat liberated or absorbed between the start of a reaction and its end, this quantity may be important in such fields as power plant engineering because one needs to know how much heat has been liberated from certain kinds of machines so that the machine doesn't get too much or not enough heat. I'm not sure how to answer it.
No, that's fine for it. Basically, it's just saying, how much fuel do they need to generate the amount of heat, say how much heat is generated by a
That
reaction.
was one of my Abraham Lincoln assassination.
What?
That was one of my Abraham Lincoln people.
Number 10, what is standard enthalpy information? How does this quantity allow us to predict whether a given reaction will be endothermic or exothermic? Chris.
I didn't know for the second part, but I said standard enthalpy formation is enthalpy charge.
Okay, so enthalpy whenever 1 mole of a compound is formed from 3 elements in their standard states. Alright, now, how does this quantity allow us to predict whether a given reaction will be exothermic or endothermic? Okay, what's endothermic?
It secretes air. No, it internal.
Okay, so it absorbs heat. So if it's exothermic, what's it doing? Generating heat. So, in mathematics, what is it, positive or negative if it's absorbing heat?
Positive.
Alright, now if it's losing heat, what symbol is it? Negative. That's one reason why scientists kind of want to calculate ahead of time to figure out, is this going to explode or is this going to absorb heat? That's part of the reason why they want to calculate out ahead and figure out, this might be a good idea. It might be safer for me to do it this way. Alright, distinguish between the heat of fusion and heat of vaporization. Ethan.
Heat fusion
Yep.
is delta H FUF fusion,
Okay.
while heat of evaporation is triangle delta H PAP.
Alright, that's the equations for it, which you do need to know. Do you know what they stand for? So like, what does heat of fusion mean?
Oh, that's what I was asking?
Yeah.
I thought that's
No, that's fine. You give the equations, so I mean you answer the problem. Alright, so heat of fusion, are you going from a solid to a liquid, liquid to a gas, or a gas to a liquid, or a liquid to a solid? If it's heat of, well, technically it's the same either way. So are you going from solid to liquid or liquid to gas if it's heat of fusion?
liquid to gas. Solid to liquid.
Solid to liquid, so heat of fusion, and then heat of vaporization, that's what?
Liquid to solid. Right?
Vaporizing.
Liquid to gas.
Liquid to gas. So remember, if you're going one direction it's positive, if you're going the other direction it's negative, but it's the same term for it. Technically, you should get more specific, but scientists don't even scientists use it that way. Alright, number 12, what is entropy? Chris?
Entropy is disorder in a system
Good job.
and is the main point of the second law of thermodynamics.
Good job. Alright, you can go ahead and put that away. Really quick, I have another set of practice problems, so it'll help you as you're getting for it. So,
Mine does
again, for this one, it's not a race. So, Quentin, I'll probably remember to email it to you later for it, but it's not a race. It goes over basically which corner is like the which corner is the largest atomic radius, the smallest atomic radius, so things like that, just making sure, are you thinking it through? And then, the best way to check electron configuration is to just practice, because you need to know electron configuration again. It's with the idea of 1s1, 1s2, 2s1, 2s2. Best way to do it is just practice it out. So, here you go. It's not a race. But if you get 100% stuck and you have no idea what you're doing, try to raise your hand and ask me. Quentin, I'll email this to you. I'll email a picture of it. practice at 1 okay yesterday?
Yes, I
Okay.
got an email.
Okay, good.
I mean, helps.
Ethan, I'm gonna say that first part we went over yesterday, so I'm just making sure that you understand what you're doing.
Yeah, but this stuff that,
But you'll know it by Friday, right?
should be.
We're not allowed to use that by Friday.
What?
We're not allowed to use that book.
Oh no, you can use the book.
Okay.
You're more than welcome to use the book. You probably will have to use it for that second part.
Guessing.
Ethan?
Crazy.
Hope you guessed correctly. Ultimately, it boils down to 50-50, because it's either bottom left or top right, ultimately. But that'd be a real bummer to miss all of them on the exam.
Not really.
It could be, depending on how many of them are on it, it could be.
Could it be bottom right?
We have not had anything be bottom right yet. Now, I could ask specifically between bottom left and bottom right,
That's fine.
but typically I don't ask it that way.
So on the right, is that P or D?
So, on the right side, which one are you looking at?
Is that P or D?
Right here?
No, like what is that? Like so there's S is the first two columns. When you're doing
where are you, so you're working electron configuration? Okay, yeah, this represents the S's, this over here represents the P's, so from group 13, 18.
Where's electron configuration?
It's in chapter 8, I think it's towards the last couple of pages, and then it also is in chapter, no, it's in the middle of chapter 8 and at the end of chapter 7, because your book's split it up weird. I agree. If I wrote the textbook, I would first of all put electron configuration much earlier in the textbook, because so much of your chemistry hinges on it.
Oh, yeah, that's where we.
Just one of those, once you get it, it's like, oh yeah, it's back to that, but hopefully it shouldn't take you too long to rework them out.
I don't know how to do it now.
Okay, we'll go over it. Alright, anyone still working in that top section 1 through 10?
Before you finished all of it.
Okay, let's go through that top section really quick then. Alright, Quentin, I'm gonna slide it
Oh.
over so that way you can see like the board a little bit more. Alright, so which corner of the periodic table has the smallest atomic radius? Chris?
Top right.
That is top right, you are correct. So that means for now number 2, which one has the largest atomic radius?
Bottom one.
Bottom
Never
left.
had that.
Alright, why is it, so thinking it through, why is it even that down here's the largest section or the largest atoms, and then up here are the smallest atoms?
Sorry, what?
Alright, why is it down here? Chris was right that down here these are the largest atoms, and then up here are the smallest atoms in size. Why?
That's what I don't really know. I had top right.
I just memorized
That's
it
right.
all the way.
You had top right as the largest? Top right as the largest?
Top right is the smallest.
Good job.
one.
Yep, and then this one is the largest. Alright, anyone remember why? You
I
could
just-
just memorize it,
I
but
just
anyone?
memorized it that one.
I'm gonna memorize them.
Yeah, okay,
If
but
that's okay.
I mean, it works to just memorize it, but it makes more sense, like so much of it, because all these ideas are related, it makes more sense to understand why it does it. Alright, Jamie, do you remember why it does it?
No.
Alright, that's fine. So, if you're going down with electron configuration, what does the numbers represent? So it's 1, 2, 3, 4, 5, 6, 7. What do those numbers represent if you're writing off electron configuration?
The proton.
Nope. The energy layer. So it's the idea of, okay, if you're starting off with one, like hydrogen, it has a nucleus, and then it has that first energy layer. How many electrons are in that first energy layer? Chris?
One.
1, so it has 1 electron. Now, if you have helium and next, how many valence electrons does that one have?
2.
2, so it has 2 in that layer. Alright, now once you have 2 in this first layer, that's as full as that one can get.
What's
So
helium's atomic symbol? He?
So once you're done, you get in the next layer, which is lithium. So lithium has how many electrons? Ethan?
Right.
Oh, how many electrons total? If you have a neutral element of lithium. So you're right, it has 1 valence electrons, but if it has 3 protons, how many electrons will it have?
3.
Yep. So this would be an example of you're drawing out an atom of lithium because you have 2 in that first layer, 1 in that second layer. That's why for electron configuration it's 1s2, 2s1. That's the reason why you're saying, okay, this first number, that first quantum layer, is telling you what energy layer that you're in. So if you're going down the periodic table, the energy layers are getting more and more. So basically you're adding on extra circles the more you go around it. So if you have, for example, fluorine is only in that second energy layer for it because fluorine starts off with 1s2, 2s, and then, I forgot where it ends, 5. So that's why for that one, and that's for fluorine. Alright, anyone have any questions about why it is the way it is now? Alright, look at the next one. Which corner of the periodic table is the most electronegative and which corner of the periodic table is the least electronegative? Alright, Ethan, let's go over to you.
The most electronegative is top right.
Good job.
The least is bottom left.
Yep. Alright, so why are these the most electronegative? What is electronegativity? I went over these terms yesterday, but it's good to remind you.
It's the ability of chemically combined atoms to attract electrons to themselves.
Yeah, so basically it's how much they want an electron. So if you're looking over here at the top right, why do these electrons want, Jimmy, why do these atoms want electrons? Jimmy?
Because that way they'll be completed.
Yeah, because remember, what does the object rule say?
They want
8 valence electrons. So up here they have 5, 6, or 7. That's probably the reason why. Because that's why up here, and since their size is so small, it's very attracted to the positive protons. They become very electronegative or very grabby in the idea of they want them really bad. Alright, you have any questions about that? Alright, which corner of the periodic table is the least negative? E and then lowercase, little subscript, EA. Anyone remember what does that stand for?
Electron affinity.
Good job. Alright, so what is electron affinity? Jamie, we'll let you define this one.
Electron water.
I do not remember.
Alright, Chris, what's electron affinity? These terms may be on your exam. I may ask you to define them. Alright, Ethan, what's electron affinity?
It's the amount of energy to add
so remember, electron affinity starts with A, so adding. So the more negative it is, the more stabilized it is for it. Alright, so Jamie, which corner is the least the least negative? I worded that really weird, but it's based on the idea of negative. So which one is the least negative electron affinity? Or the most positive, if you want to think of it that way.
The bottom left,
Good job. And then which one is the most?
top right,
Top right. Because remember, which ones are stabilized by adding on electrons?
the top right.
The top right. So that's the reason why. If you were to add on electrons to these down here, Chris, do they want them? No. So that's how come those are not more negative or not more stabilized because they don't want them. So they will become unstable by adding them on. Alright, anyone have any questions about that? Alright, which corner of the periodic table has the lowest ionization energy and which one has the highest ionization energy? Alright, Ethan. Alright, first of all, what is ionization energy?
It's the energy, amount of energy to lose electrons.
Yeah, so amount of energy to take an electron off. Okay. So which one has the lowest ionization energy?
Bottom left,
Bottom left. And
Top
what
right.
is the highest then?
top right.
Top right. Why?
Because the ones on the bottom left want to lose.
Yeah,
the
so
electrons.
these are the largest metals, and so because of that, they don't want their electrons, so it doesn't take a lot of energy to take them away. While these up here, do they want their electrons? Yeah, so it'll take a lot of energy to pull them off because they don't want to lose them. Alright, number 9 and 10. Which corner of the periodic table has the most metallic character, which has the least metallic character? Chris?
Bottom left.
But, okay, for which one?
Metallic, most metallic.
Yeah, most metallic character is bottom left, and then the least metallic character is top right. Why?
Because the left are the metals.
Okay, so why is it bottom left and not top left?
Because the metals are the left.
But why is it bottom left and not top left?
Because metals want to lose their electrons.
Okay, but why is it bottom left and not top left? Because they're both metals. Based on your answer, you're still not given it. What's the difference between these metals and these metals down here that make these want to lose them more? Or make them want to have higher metallic character?
More protons?
What?
More protons?
Close. What else are they if you're going down on the periodic table? What do the different periods represent as you're going down? If you're writing electron configuration.
I don't understand.
Alright, so if you're doing
I'm sure I know it, I just can't think, I just can't say it.
Alright, well you gotta be able to at least write it out in the exam.
Yeah.
So, if you're doing an electron configuration and you're in this line, what energy level are you in? Or what's that first quantum number?
1,
Alright, what are you going on here?
2,
We're going on here.
3,
Right?
4, 5, 6, 7.
Okay, so what does the first quantum number represent?
Subshells? maybe?
Nope.
No, shell energy.
Energy layers. So the number of circles or energy layers is increasing. So why do these down here, back to my original question,
Because they're further stretched out.
yeah, because they're larger or they're farther away. So that's the reason why they have a lower ionization energy, and since metallic character is based on low ionization energy, they say that, okay, since these have the lowest ionization energy, they have the highest metallic character. Alright, anyone have any questions about why something is the way it is? Alright, electron configuration. Alright, Chris, you said you finished all of them, so why don't you go ahead, oh, you got them all? Okay, good. So we'll let Chris start off then. Alright, so for this one, I'm just gonna let you write it in the abbreviated version because that's the faster way to do it. And
It
so
says use the abbreviated.
What?
It says use the abbreviated method.
that's what I said. That's why I said you put here on the abbreviated method because it's the faster way to do it. But if
No,
you
I
need
mean,
help,
yeah.
we can go through all of it. But I just
No.
know for this, wait, I just know for this one, it's the faster way to
Are they
check.
all
And if you're
both?
and if you're struggling with it, then it's a good check for it now. Okay.
Are they gonna want both in the exam?
I believe they only ask for the abbreviated one, but if you can't get the abbreviated one, then we need to go back and double check the other one as well then. Okay, Chris, what do you got for the first one? For aluminum.
3s2. Or any first.
I was about to say, okay, we're missing something, but I'll go back and check in a second.
And then IP1 or 1P1, 1P2. Or 3P or 2P2. 2P1. 2P1.
Sorry. Alright, anyone agree with this answer?
Not me.
Okay, Ethan, what do you say is different about it?
It's 3P1.
It is 3P. So keep in mind that the S and the P's, their numbers match up for it. So for this one, that this is 1s1, 1s2, 2s2, remember P only appears in that second layer. There is no 1p. So that's why this one is 2p6. Jumping down here, 3s2, 3p6. Alright, anyone have any questions, or do you have any questions, Chris, about how to do that?
No.
Alright, anyone have any questions about this first one? Alright, Ethan, we'll let you take the second one. So iodine.
KR,
Good job.
5s2, 4d10, 5p5.
Alright, is that it? Anyone disagree with this answer?
Is it wrong?
Yes, it is.
Alright, what's wrong with it?
2D, not 4D.
Why is it 2D?
Because it's only the second D.
Okay, well keep in mind that D only appears in that third energy layer for it. So for this one, if this is 1, 2, 3, 4, 5, that this one only appears in the third energy layer. So this is 3D, this is 4D for that one. And so actually, Ethan has it perfect, so that is correct. I just wanted to make sure everybody else had the answer as well. Does anyone have any questions though about this? But you did get it perfect, Ethan. Alright, Jamie, next one. Cobalt, what do you got for that one?
AR gonna have 4, 6, 2.
Sorry, say that again?
It's 4, 6, 2.
6?
Oh, S.
Okay, I'm gonna say, okay, I'm not sure what that is.
And then 3D7.
Alright, anyone disagree with this answer?
I have that.
Yep, this is correct though. Anyone have any questions about it? Alright, well let's see, I think Quentin can see these. Alright, Quentin, I'm gonna go ahead and erase this. I can save space. Alright, so F, anybody want it?
Me.
Alright, Ethan.
HE, 2s2, 2p5.
What was it? This was the last one?
5.
Alright, anyone disagree with this answer? Alright, good job for it. So I actually copied down the wrong one, but yeah, that is the correct answer for it. I'll fix it in my answer key. Alright, anyone have any questions though about it? Alright, last one, barium. Anybody want it?
Me.
Alright, Ethan.
XE, 6s2.
Yep. Alright, anyone have any questions about how to do this? Because it is going to ask it on your exam. Alright, we can spend the last few minutes reviewing, then we're going to play this kind of quick for it. So, that's a good review though for chapter 8 and starting getting into it. Yes.
What time is the class in?
This class ends at 55, so we have about 15 minutes. So we could probably play at least one round of this, maybe a second round. Alright, so go ahead and get out a piece of paper so we can write down terms and definitions you don't know as we get into it. So hopefully you still have the same piece of paper from yesterday, so that way you'll save your time as you're studying for it. I'll do that kind of like a cheat sheet as you're going through it. Alright, since Jamie's by herself, we'll let her go first. Alright, Jamie, so thinking about in chapter 7, this is with light, electrons, and atomic structure. Alright, what do you call the high point of a wave?
The crest.
Good one, what's the bottom part of the wave?
Trough.
That's it. Alright, yes, Chris.
Two things. Are we gonna have homework tonight?
Maybe?
Okay, I just didn't know
Wednesday.
if I can like pack this up.
Alright. Well, you might need it.
I don't have to, but can I sharpen my pencil?
You may sharpen real quick. Alright, Jamie, fix that.
7.
Alright, play one. Alright, we'll let Ethan go first. Alright, Ethan, what do you call the corresponding points on a wave?
Wavelength.
Good job. Oh, do you remember what's the symbol for it as well?
What's this?
It's a Greek letter. It looks kind of like an upside down Y.
Hertz.
Nope.
Okay.
Alright. Nope.
I don't
What was the
know.
question?
Alright, what's the symbol for wavelength?
Lambda.
There you go. Lambda. Alright, fix that.
Oh, hold up.
1.
Okay.
Well, it's technically Ethan's question. We'll
Yeah,
say gravity applies.
I'm a smarter
at least this
person.
time. Well, Ethan got both parts actually before you.
What?
He got both parts before you.
I'm saying like with strategy, I'm a smarter person.
I think that's up for debate on your teammate, but don't insult your teammate. Alright, Ethan, what color do you want to be?
Gray.
Alright, we'll be Christmas colors. Alright, back over to Jamie. Alright, Jamie,
Gray.
what is, let's see, what is considered the wave's height? It's also a measure of the wave's strength.
Amplitude.
Amplitude. Alright, big spot.
6.
Alright, what is the number of waves that pass a point in a given time? This is Chris's turn.
Wave frequency?
Say it one more time.
What's the wave frequency?
Frequency. And you remember what is the SI unit for frequency?
Velocity.
Like what is the unit for it?
Hertz.
Hertz.
8.
Alright, let's see. Who came up with the particle theory of light?
Me. Was it Newton?
It is Newton.
T.
Alright, who came up with the wave theory of light? I think it's Ethan's turn technically.
What's this on?
H for last name. We're back in that scientist chapter.
I know it is.
Is it Christian?
Mm-hmm.
Christian. What is it?
Isn't it like Heisenberg?
You're thinking of Heisenberg uncertainty theory?
Hyman.
It's not Heisenberg.
Hyman.
I'll take that. Huygens. Alright.
Z.
Alright, over to Jamie. Alright, who proposed the electromagnetic wave?
Maxwell.
Maxwell. So James Clerk Maxwell.
You.
Alright, what is the speed of light in a vacuum?
My turn?
Yep.
3 times 10 to the 8.
You don't meters per second.
5.
Let's see. Alright, what is an arrangement of all forms of electromagnetic radiation in order of frequency and wavelength? What do we call that full list?
The electromagnetic spectrum.
Yep, that's it.
9.
Alright, what do we call the tiny bundles or packets of energy according to the quantum theory of light? What do we call those tiny bundles or packets of energy?
Photon.
Photons.
You can pick whatever, just don't pick 2.
Okay. What do you want to pick? You pick.
Why?
That's what I was going with.
Yeah, I agree. Alright, back over to Jamie. Alright, Jamie, let's see. If I increase the frequency, what's gonna happen to the energy of the wave?
The energy of wave.
Mm-hmm.
Will it get higher?
It will increase as well because it's directly tied to frequency. Right. What is a device that's used to measure, that's used in the laboratory to separate the colors and study them in detail?
Let's
Starts with an S.
spectrometer.
Yep, spectrometer.
And
Alright, Jamie, so back to the scientist. Who proposed the plum pudding model first?
The plum pudding model.
Mm-hmm.
Was that Thompson?
That is Thompson, J.J. Thompson.
3.
Alright, who proposed the planetary model?
Rutherford.
That's Rutherford.
W.
Alright, who proposed the idea that they're locked into these energy levels or these orbits? Alright, this team has a chance to steal basically.
say it again.
Who proposed that they're locked into these energy levels or orbits? What?
Board.
Bohr. So make it up him. So Niels Bohr. Alright, fix back, Chris.
Pass.
Alright, what do we call?
We're not ready.
I'm sorry. Alright, let's see, what do we call it whenever you have the electrons in that lowest energy state? What's that term?
The ground state?
Yep, what's everything above that?
An energy state.
Alright, you got half of it, so I'll let you have it, but
Half it.
excited.
Excited.
Excited states, I'm sorry. Excited states. Alright, Jim, big spot.
M.
Alright, back over to y'all. Alright, who proposed matter waves? Last name technically is with a D, but with a B more.
Dave Broglie.
I think you stole Jamie, so I think it's Ethan's turn.
Dave Broglie.
De Broglie. So Louis De Broglie.
What do you want to do?
Alright, let's proposed the wave mechanical model with the idea of a standing wave? Weird last name, starts with an S.
Schrodinger.
Yep, Schrodinger.
Cute.
Let's see. Alright, who proposed the uncertainty principle? They're the idea you can't know the momentum and the velocity at the same time.
Starts with an H.
Starts with an H. Huns?
Oh wait, the Heisenberg.
Heisenberg. So this is Heisenberg uncertainty principle.
We go.
Alright. Who proposed the idea of orbitals with the electron cloud model, saying they're not locked into these lines, it's more of a region because they're going up and down at the same time?
What does it start with?
It's the last name starts with a B.
Born.
This is the Born one. So Max Born.
B.
Oh, you're right. Gotta go around. Alright, so what do you call the complete arrangement of electrons in an atom?
Complete electromagnetic spectrum.
What did you write?
Spectrum.
What do we call this whenever you're writing off the electrons?
Electron configuration.
There you go, electron configuration.
P.
You agree. Alright, there are the 4 quantum numbers to describe the placement of the electrons. What's the first one and what's it describe?
First one, the energy state, and it's the principal quantum number.
Yep, it's one and it describes the energy level or the electron shell. Okay.
G.
Alright, so what's the second quantum number? What's it describe? I think it's Chris's turn.
No. I know.
Second quantum number, what's it describe and what is its name?
Doesn't it describe a shape?
Alright, yep, it describes the subshell like shape, but then also what's the name for it?
What's the?
S.
Give it to me.
Right?
Subshell.
Subshell. So it's the subshell quantum number and describes the subshell shape.
H. No.
Oh, we'll say this is still white. Okay,
J.
this is still white. Alright,
No,
what
we're
is...
not red.
We're green.
Oh, I'm sorry. Alright, Jamie, what is the third quantum number and what does it describe?
It describes the orientation in space.
Good job.
And is it just called the third quantum number? Or this is the name of the third quantum number?
There's a name, there's a more exact name for it. Its name is a little bit confusing though, because it doesn't sound like what it describes.
Is it like the magnetic state?
Good job, magnetic quantum number.
B.
B.
Can't be B.
Oh yeah, this one's not here, they picked it by accident.
Okay.
Alright, so over here, what is the name for the fourth quantum number, what does it describe?
It's my turn.
I think so, because Ethan helped you out.
The fourth quantum number.
I know it.
Spin.
Is that the, what it describes or the
Yeah,
name?
it describes.
Okay, it describes the electron spin in
the
theory,
spin
that's the best way to think of
It's
it?
a spin quantum.
Yep, that's
B.
all.
We win.
What?
We're green. We win. SNID.
Oh, good job, yep.
We were the one either way. We had 3 ways to do that.
Alright, we'll play one more time and we'll say, do you wanna try to all be independent? I don't think it's gonna go well, but do
We
you
only
wanna try?
have 5. I think
Yeah.
We only have 5 minutes though.
Yeah, do you wanna try to be independent or do you wanna try to stay in teams?
Might as well just try to be independent.
Okay, we'll try being independent. We'll let Ethan go first for this one. Alright, Ethan, if I have
Gravity apply.
we'll see, gravity does not apply, we might as well just throw all the rules out the window and just see how this goes. Alright, so if I have an S orbital, what shape do I have?
Sphere.
Alright, and then if I have a P, what shape is it?
Dumbbell.
Good job. If I have a D, what shape is it?
Double.
Good job. Alright, pick your spot.
1.
What color you want to be?
Blue.
Alright, we'll stick around. So, Jamie, going back over to you. Alright, what is the principle that states that no 2 electrons in an atom can have the same set 4 quantum numbers?
Is it the Aufbau?
Not Aufbau.
Also.
Is it the Pauli exclusion?
Pauli exclusion principle.
O, purple.
Alright, Chris, what is the principle that says they will occupy the lowest energy orbital available and then work their way up?
Law of octaves?
Nope.
Octet?
Nope.
Let's start with
A. Oh, no. Yeah, that's
Seven.
it. Alright, 7.
no,
What color you
8. No, yeah, 7.
Let's do it.
What color you wanna be?
7. I'll be the random, just face on
You should be this neon yellow now. Alright, Ethan, what is the rule that says whenever P, D, or F subshell is being filled, they'll fill 1 in each orbital spot before they go back and repair up?
Start with H.
Starts with an H.
Hunch.
Hun's rule.
Q.
Alright, Jamie's turn. Alright, Jamie, what do we call the outermost electrons?
Valence electron.
Yep. D. Is that D? B. Okay. Alright, what's the difference, Chris, between a Lewis symbol and a Lewis structure?
A Lewis structure is like what you draw up on the board, and a Lewis symbol is the dots.
Yeah, that works. Okay.
Let me go 6.
Gotta find it. You were neon. Alright, that's pretty much all of chapter 7, so that was good. Got through most of that. Alright, chapter 6, thinking back over it. Alright, what do you call energy of motion?
Kinetic.
And then what is energy that's not being used yet?
Potential.
Good job.
3.
Alright, what is the area of chemistry that deals with applying thermodynamic principles to energy changes in a chemical reaction?
Thermodynamic.
Area of chemistry.
Chemical thermodynamics.
Chemical thermodynamics. H. Let's see. Let us see how far we can get. Alright, Chris. What is the law that says that energy is neither created nor destroyed? It just changes forms.
Thermodynamics. Law of thermodynamics.
Which one?
The first one?
It is the first one.
Yeah.
Easy over.
So let me get there eventually. Alright, Ethan's turn. Alright, Ethan. Let's see, we've gone over that already. Alright, anyone have any questions about how to find specific heat as a side note with the oh, you know what? What's the equation to find specific heat? Sorry, Ethan. So, little c equals
Q.
good job.
Over delta H. H delta. T delta. H D. Oh, H delta T.
Nope.
C. Q. No. What's
How much stuff is there? Like, what is the unit to measure how much stuff is there?
to start with?
In.
Mass.
Alright, pick a spot. You got a hard one.
U.
Alright, the bell's not gonna ring because it's early, so you don't have any homework, but if you wanna look over in the gas laws in chapter 5, come with questions tomorrow if you have no idea what you're doing, or you'll go over and go, ooh, I don't remember that, then come ask me tomorrow, or let me know today so I can fill out practice problems. Alright, you are dismissed. Bye.